Okay, in this video, we're actually going to talk about two new tests. We're going to talk about the integral test and the p-series test. The p-series test is based off the integral test, so they kind of go together. So let's consider this series, 1 over n squared, the summation from 1 to infinity, which generates 1 plus a fourth plus a ninth plus a 16th. It's just the reciprocals of all your perfect squares. If we think about the other tests we've learned so far, the nth term test, if you took the limit of 1 over n squared, you'd get 0. We know that tells us the test fails. Clearly, it's not a geometric series. You're not multiplying by the same number to get from one term to the next. The sequence of partial sums is always an option, I guess, for a series, but it kind of depends that you would be able to add a bunch of terms and figure out a formula for the sum of the first n terms. And that's not always easy. You might explore it and see, try adding the first 2, 3, 4, 5 terms, see if you notice any pattern, but it may not work out so well. So let's look at this another way. These two pictures are going to be very, very useful, and they should look familiar from 21B when we were doing Riemann sums, putting rectangles under curves to estimate area. Notice what I have here is I'm using, for this one, I'm using left endpoints for the graph of y equals 1 over x squared, which I'm looking at because I'm trying to learn about the series 1 over n squared. Okay, it's a decreasing function. So if I use left-hand endpoints, the areas of those rectangles, which notice those are exactly the same as the terms in my sequence. Why? The widths are 1. The height of my first rectangle is 1 over 1, which is 1. For my second rectangle, I'd get an area of 1/4, 1/9. All the way. Now to capture my nth rectangle, I have to go to n plus 1. Now the second picture, I'm using right-hand endpoints and I'm getting a lower bound for all of the terms except for my first term, right? Because to do a right-hand endpoints, I'm gonna actually be using, my first rectangle would represent a sub 2, would be the second term in the sequence. And what we can learn from these pictures, if you go back to the upper sum, a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n, that's what we mean by the nth partial sum. And clearly, because those areas of those rectangles is greater than the area under the curve from 1 to n plus 1, the nth partial sum is always going to be bigger than the integral from 1 to n plus 1 of f of x. F of x being the function that is associated with your series. If I go to my right picture and take out the first term, then clearly a2 plus a3 plus a4 all the way up to a sub n would be less than the integral from 1 to n of f of x. So if that's true, and then you just imagine adding a1 here and a1 there, that's going to be true as well. So what we have, we've sandwiched or squeezed the nth partial sum between two integrals, okay? And we can use that now. If I want to have an idea of what the 100th partial sum is for 1 over n squared, 1 plus 1/4 all the way up to 1 over 100 squared, well, the value of that sum has to be between the integral from 1 to 101 of 1 over x squared, but also less than a sub 1, which was my first term, plus the integral from 1 to 100. And if you work that out, okay, do your antiderivative, plug in, same thing on the right side. We can find out that the sum of the first 100 terms has to be a number between 100 over 101, so pretty close to 1, and 1 and 99/100ths, which is pretty close to 2. So the first 100 terms have a sum that is somewhere between 1 and 2. Now, from this picture, what we learn is that anytime I'm studying a series where the function associated with it is a decreasing function, like this, right? Decreasing towards zero. This, I could always draw these two pictures. These two pictures would always look the same. You know, the function might change, but this inequality is still going to hold true as long as my function is, okay, as long as my function is positive, continuous, and decreasing, okay? Let's go back up here. From that picture on the other page, we can see why we would expect 1 over n squared to converge, because other than the first term, so here's what we're going to focus on. Okay. This is the sum of my series up to the first n terms. So if I were to go to infinity, if I wanted the infinite sum, as if this integral converges from 1 to infinity, then we know our sum would be less than some number here. That would show that our series has to converge. Conversely, suppose I was actually studying a divergent series. Then what would happen is this integral would probably diverge. If it was a divergent series, this would diverge, meaning it was infinity. And what I could then state is my sum is greater than infinity, so I would know my sum is divergent, okay? So this inequality can be used to show that if the integral associated with your series converges, so does your series. If the integral associated with your series diverges, then your series would diverge as well. Again, as long as we're talking about a positive, continuous, decreasing function, as long as it's decreasing for some value less than infinity, for x greater than some number n. Okay, it doesn't have to be decreasing all the time, but just from n onward, from some positive number onward. Now, 1 over x squared from 1 to infinity does converge. You can confirm that. That's a 21b integral, which means 1 over n squared would have to converge as well. Okay, let's look at another series here. The summation from 3 to infinity of ln of n over n. And I just put like this, you should be thinking about this. Could I prove it with the nth term test? Well, if I took the limit, we know that n gets bigger faster than ln of n, so I would have gotten 0, so that won't help me. It's clearly not going to be geometric. And again, if you want to try to find a formula for the sequence for the nth partial sum, go for it, but I don't think it's going to work out so well. The next question then you might ask yourself is, can I integrate ln of x over x, the function that's the same as the formula of the sequence of my series? And hopefully you realize, yes, you can, right? So then that suggests that we could probably use the integral test. We do have to make sure that our conditions are satisfied, right? We know the integral test only works if we're talking about positive, continuous, and decreasing terms. If we're going from 3 to infinity, ln of n and they're both going to be positive, so I think we've got that. Clearly, these are continuous functions from 3 to infinity, so that's fine. The only thing that maybe we need to show here is, does this generate decreasing terms? So one way we can confirm that, if you go back to 21a, if you took the derivative of that function, which I did here using the quotient rule, I found out my derivative was equal to 0 when x was e, and using a little sign chart, I now confirm that my derivative is negative as long as x is greater than e, and it's always going to be negative after that. So then that proves f of x is decreasing for x greater than e, and that's what we mean by n. As long as it's decreasing for some number, positive number from then on out, then the integral test is valid to use. So we've satisfied all the prerequisites for the integral test, so we'll go ahead and integrate. This is a 21b thing now. Recall you would do a u sub, let u equal ln of x, du is 1 over x, which is sitting right there. So this is just the integral of u du, which integrates to u squared over 2. And if you replace your infinity with a b, plug in b, and take the limit. This term's going to go to infinity, which means the integral diverges. And since the integral diverges, so does your series by the integral test, okay? By the integral test. Okay, let's look at another one. I got the summation series of e to the n over 1 plus e to the 2n. I could run through and, nth term test, you're going to have a bigger infinity on the bottom than you do on the top, so you're going to get 0. That's not going to help. Can I integrate this? Well, yeah, with a little thinking about it, you actually can integrate that. It's actually an inverse tan integral. Clearly, it's a continuous function, right? The top and the bottom are both continuous functions. E to any power is always positive, so we know that's true. And sometimes it's pretty obvious that this denominator is going to get bigger faster than the numerator. So it's going to be decreasing when n is greater than 0. I put check if you want. You could take the derivative of this like we did on the last one and show that the derivative is negative for n greater than some number. Okay, then as long as it satisfies those 3 requirements, we can do the integral. This is the sneaky part. You have to think of e to the 2x as e to the x squared and do a u sub. And it's going to turn into 1 over 1 plus u squared du, which integrates to inverse tan. And if you replace your limits b to 1, let b go to infinity, you get the inverse tan of infinity, but be careful, that's not infinity. What angle has a tangent of infinity? That would be pi over 2 minus the inverse tan of 1, which is pi over 4, so I get pi over 4. So we know the integral then, because we got a finite number, converges, so therefore the series does. Be careful, I don't claim that the sum of the series is pi over 4. That's the value of the integral. That doesn't mean it's the same as the sum of the series, okay? Now with the integral test, we actually get another test kind of for free here. If you have a series that's 1 over n to a power, my very first example, 1 over n squared, which I gave, it would be an example of this. We call that a p-series. And a p-series like this, if p is a positive power, is going to satisfy all 3 requirements: positive terms, decreasing, and continuous. And if you do an integral test for 1 over n to the power, you can show that it will always converge if your power is bigger than 1, and it will diverge if your power is between 0 and 1, including 1, okay? And so this can be a really simple test as well, probably one of the easiest. If you see 1 over n to the 5th, your p-value would be 5, greater than 1, we can automatically say that we know this series will converge by the p-series test. If I have 1 over the cube root of n, my value of p is 1/3, which is less than 1, so I know it would diverge by the p-series test. That's it. Don't have to show any more work. Okay, so that's kind of nice. One other thing about this integral test is we can also use a picture similar to the one we drew before to put an estimate on the error. And what I mean by that, let's go back to 1 over n squared. If you do add the first 4 terms, s sub 4, you will get 205 divided by 144. By the way, 1 over n squared has a p-value of 2, right? And so using the p-series test, because p is bigger than 1, I know that this series converges. So if it converges, maybe we're trying to find an idea of what the sum is. If I add the first 4 terms, I get 205 over 144. Let's say I want to know what my error is. How far off is this from the actual sum? So I want to put an upper bound on the error. And so notation-wise, here's what we do. S sub 4 is the sum of the first four terms. R sub 4 is the error. That would be all the remaining terms that we're not adding to this, right? R sub 4 is the remaining terms. That's where it gets the name R, which could also be thought of as your error, right? This is your error in this, right? Error in S sub 4. Now, from the same two pictures that we drew earlier, if you continue them, if you go back and look in the video, we stopped the first one at n, but if I kept going, actually here was a sub n. This would be the sum of the first n terms. My remainder would start here. My remainder would be the next term after the nth term, a sub n plus 1 plus a sub n plus 2 plus a sub n sub 3, and so forth. So your remainder are those terms. Clearly, from this picture, R sub n is greater than, those rectangles are above the integral from n plus 1 all the way to infinity of your function. And looking at your lower sum, my first rectangle is actually a sub n plus 1. And so clearly R sub n, a sub n plus 1 plus a sub n plus 2, and so forth, is less than the integral from n to infinity. So we can put a bound on this now. If I used the first four terms to try to estimate the sum for 1 over x squared, I know using this inequality that the error, R sub 4, has to be greater than the integral from 5 to infinity, but less than the integral from 4 to infinity of my function. If you work this out, okay, you have to integrate and plug it in. I know you guys can do that. You got 1/5 here and 1/4 there. So what does that mean? That means if I use 205 over 144 as the sum of this series, my error, the true sum, is no more than 1/4 to 1/5 off from that, right? So the true sum of the series, if you think about it, has to be between 205 over 144 plus 1/5, that's my lower bound on the error, or no bigger than 205 over 144 plus 1/4, my upper bound on the error, okay? An interesting thing, this isn't something you have to know, but this is just kind of an interesting, cool thing. The actual sum of this series, okay, this is side note here. It's been shown, and it's kind of a cool proof. I have a outline of it in my on my notes online. The actual sum of this series has been shown to be pi squared over 6. So what is pi squared? Pi is like 3.14. So this is 9 point something over 6. It's about 1.5 something, right? 1.5 something. Now, what's kind of interesting about that? Whenever you see pi, right, up before you get to calculus, every time you see pi, we know we must be thinking about a circle, right? Pi is always, the area of a circle is pi r squared, the circumference is 2 pi r. And so it's a little surprising, right? This series, which involves the reciprocals of the perfect squares, what in the world does that have to do with the circle, right? Well, there is a connection. There is actually a way of looking at part of a circle and seeing this infinite sum. And so that's one of the things that's kind of neat sometimes, and why pi, okay, I know all of you have probably had a math teacher who gets really excited about pi. I know that a lot of times in my teaching career, I've kind of gotten strange looks from students. Okay, pi, it's cool. The area of a circle is pi r squared, the circumference 2 pi r, big deal, right? What's the big deal? What's interesting about pi is a lot of students who don't get to calculus don't realize this, is that it's a number that just seems to show up in unexpected places, right? Who in the world was expecting this sum to have anything to do with pi? But it does. It just shows up there, right, as the sum. And so these are the kind of things that keep math people interested. I just wanted to share that cool fact. Okay, the next video we're going to look at two more tests, the comparison test and the limit comparison test.